All right, we're ready to roll. Today we're going to talk about filtering. As you can see, you live in a barn.
No, they're right behind me.
I don't care. Please close the door. Today we're going to talk about time and frequency domain. We're going to talk about Fourier analysis, and we're going to talk about filtering. Those are going to be the three main topics. Of course, they all relate to one another. But some of this you may not have had. Some of it I know you have had because I've seen the worksheets that you all are working on regarding the different types of filters. But as I like to do in these type of things, I want to take a step back and kind of justify some of the things that you all are doing and take a look at what filtering really is and how we accomplish that, and look at some different ways to analyze circuits and waveforms and whatnot to see what the effect of filtering is. The question comes as to why does filtering work? How come a capacitor has the ability to filter a waveform? What happens to a waveform when it is filtered? And how can we change these things or adjust these things to be able to filter out and filter in different types of waveforms? So we're going to get to the low pass and high pass, band pass and band stop, but I want to give you guys some preliminary information that's going to prove valuable when you get into the AM and FM that you're going to be studying in the next couple of weeks. So, what instruments have you used in your lab? You've used a voltmeter, right? What else? Oscilloscope.
Function generators.
Function generator. Anything else? Power supplies.
Potentiometer.
And all potentiometers, all those fun little parts and pieces. Oscilloscope. Let's talk about an oscilloscope first. What does an oscilloscope show you?
Frequency and time.
It shows you what?
Frequency and time.
You sure?
Yeah, because you get the time and then you get your frequency.
It doesn't show you frequency.
It shows you volts peak to peak.
Well, you got to calculate it, yeah. But
Then it doesn't show it, right?
Okay, yeah.
It gives you information that you can use to calculate the frequency, but it does not actually show you the frequency. On an oscilloscope, in the x direction, what is on the x-axis? Time. And what is on the y-axis? Volts, or amplitude, which is just another word for volts, right? And so if we want to look at a sine wave on an oscilloscope, it's going to basically look like the traditional sine wave that we see, right? No surprise, we've all seen that before, right? This is what we refer to as the time domain. Okay, it shows the amplitude with relationship to time. How does the amplitude change over time? But that's only half of the picture, because we can also look at signals in what we call the frequency domain. And if we look at a signal in the frequency domain, we're going to have amplitude on the y-axis, and we are going to have frequency on the x-axis. Okay? And the device that we would use to analyze something in this nature is called a spectrum analyzer. And yes, we do have a couple of those here. They're very expensive, and we usually don't pull them out until later in the term when you all are messing around with your radios and getting into modulation. So you can kind of look at this as the introduction, if you will, to modulation, because modulation in radio, all that stuff is all about filters. Okay? When we tune in a radio station, what are we doing? We're taking a bandpass filter and sliding it up and down the frequency range to allow a certain frequency to get through. Okay? In the spectrum analyzer, this same sine wave, and let's just say that this is 1 kilohertz, and let's say it has an amplitude here of A from maximum to minimum. That sine wave is going to look like this on a spectrum analyzer, where this height right here will be equal to A. It's just going to be a single spike. Okay? That's normally the type of thing that you see. Now, jumping ahead, which I'm not going to do much more of, but when you look at an AM radio station, it typically looks something like that. It has what we call sidebands. It has the carrier along with 2 sidebands. That's in your future, but this is going to become something that's very familiar to you. And the reason it's familiar is because we need to be able to look at it this way in order to tell exactly what's going on. In an oscilloscope, the waveform will not be as obvious. It'll be very difficult to calculate or determine what the frequencies are. Okay? When we look at an oscilloscope display, what we're looking at, again, is amplitude over time. It works great for when we look at a waveform just as a waveform, but when we look at a complex waveform and we want to find out what that complex waveform is, we have to use something called a spectrum analyzer to be able to do that. That allows us to plot amplitude versus frequency. Okay? Now, I guess the question would be, why is that important? And really, it's because of what this dead guy came up with. This guy, Fourier, long rest his soul, came up with a really interesting statement some time back. And that statement was, and this is going to probably be important, so you might want to jot it down, and that is that all waveforms, no matter how complex they are made up of a combination of sine waves. Okay? All waveforms are made up of a combination of sine waves. And the same thought that all material is made up of what?
Matter.
Atoms?
Yeah.
Atoms. Okay? All waveforms, no matter how complex they are made up of sine waves. And I'm going to give you 2 examples of how that works. So we're going to be working today in the time domain and probably more in the frequency domain. So this is going to be our friend today, is this type of graph over here, where we're plotting frequency versus amplitude. All right? Any questions so far? Can I erase what's on the board? You need a little time to copy that, sir? Can you get it from someone else?
Yeah, okay. I'll give it to someone.
Okay, basically all we're doing is looking at 2 different ways to view a sine wave. This one you're familiar with on the oscilloscope, right? You've seen this before. This one you've probably never seen before. Anything like this type, where it's just an individual sine wave is nothing more than a spike. That's the only sine wave we have in this display. So you can almost look at it as though you're looking at it from the side, like there's a z-axis coming out of the board, and you're looking at it out at the side. Okay? Let's talk about a square wave for a minute. I'll leave that up there for your reference. In the time domain, a square wave looks like this. And let's say that this is 1 kilohertz. One of my favorite frequencies is 1 kilohertz. Why? Anybody able to answer that question?
It's easy to work with.
It's easy to work with in what way?
Calculating things.
Well, in some cases, calculating it is a lot easier, but I don't really care about how hard calculations are. That doesn't bother me. The reason I like working with 1 kilohertz in a lab situation is because, number one, I can hear it. Number two, it's not so high or so low as it's annoying. It's just a fairly generic tone. You know, 1 kilohertz isn't too high where it messes with your ears and stuff. And it's low and high enough as to where you can hear it. So 1 kilohertz is really a good test signal, especially for audio types of things.
So,
Okay?
it's good because you can hear it, and what was that again?
It's good because you can hear it, and it is not so high that it just gives you a headache to listen to. It's fairly pleasing. It's not really, I don't know what the word annoying, I guess, might be the word to use for that. So we'll pick 1 kilohertz. That means that this amount of time is how much? How much?
That would be divided in half.
Well, if the frequency is 1 kilohertz, what's the length of 1 cycle?
You don't have any divisions of it.
I don't need any divisions. Did you do a formula that says that the period of a waveform is equal to 1 over the frequency? Yes. The frequency of a period is 1 over the the period. What am I giving you?
1 kilohertz. 1 over.
Which is a
1 over
frequency.
Yes.
1 over that would give you your time.
So what would be the period? Where's your calculator, sir?
In my bag.
Ah.
1
milli.
1 milli banana? Milli vanilli? 1 millisecond. Okay. So where did that square wave come from based on what we just said?
I'm gonna grab my calculator real quick.
All right. Where did it come from based on what we just discussed about Mr. Fourier?
Combination of sine waves.
Came from a combination of sine waves. Okay? Do we have any idea what combination of sine waves would create that? And the answer is yes, we do.
Okay.
We can easily manufacture a square wave by adding sine waves together. And I'm going to show you how that works. What we're going to do is we are going to take a 1 kilohertz sine wave, 1 kilohertz sine wave with an amplitude is equal to A. We're going to add to that a 3 kilohertz sine wave, and I'll get to the bottom of this math here after I get this done. With an amplitude of A divided by 3. So it's going to be 3 times the frequency and 1/3 of the amplitude. We're going to add to that a 5 kilohertz sine wave, which is going to look like this, at an amplitude of A divided by 5. We're going to add to that a 7 kilohertz waveform, sine wave, which is even smaller and more squunched together with an amplitude of A divided by 7. And we're going to add to that all of the other ones. 9 kilohertz, 1/9 of the amplitude, 11 kilohertz, 1/11 of the amplitude, 13 kilohertz, 1/13 of the amplitude, and we can continue to add all of those waveforms together. The more of those we add together, the squarer our corners become.
Is there a reason why you're using odd numbers?